In this video, we're going to look at another theorem that's going to be used for reasoning for the explanation for certain free response questions, and that's the mean value theorem. So here's the statement of the mean value theorem. It's a little confusing, all right, but I bolded the most important things. Let f be continuous on this closed interval and differentiable on the open interval. So if it's continuous and differentiable, all right, then there's a point C on the interval such that this happens. The derivative at C is the same as the formula here, and if you recognize this as the y values or the x values, this is the average rate of change. So the mean value theorem says if you have a continuous differentiable function, there's some instantaneous rate of change that is exactly equal to the average rate of change. All right, so let's see what this looks like in a picture, because the picture makes a lot more sense. All right, so let's pick some random A and B. Let's pick like A here. All right, so this is A, and let's pick, I don't know, B here. It doesn't quite matter because it works for anything that's continuous and differentiable, which this function is. All right, so the average rate of change we know is the slope of the secant line. So the slope between these two is the average rate of change. And the mean value theorem says there's the derivative, an instantaneous rate of change, a tangent line. All right, so all those things mean the same thing. That is the same as this. And if slopes are the same, they're parallel. So there should be some C value with a tangent line parallel to this. If I think about it, it's going to be about there. Oops. All right, this looks like it's going to be my C value. If I have the tangent line there, it kind of just scoots along the edge of my graph. All right. And I might have missed it a little bit. It might actually be like there. But you can see the basic idea. I have this secant line. That's the average rate of change. All right. Oops. And I have my tangent line. That's the instantaneous rate of change. And the mean value theorem with this continuous and differentiable function guarantees these two will be parallel. All right, not this specific, it guarantees there is a C that's parallel. All right, and we can do it again. Let me just kind of erase all this. And let's pick a different A and B just to show. Let's pick the very ends, this A and this B. All right, so we have our secant line. We should be able to find a tangent line that's parallel to that, and it looks like right around there. All right, that point there looks like it has one, and actually get another one down here. All right, the mean value theorem just guarantees there's at least one. There could be a bunch of them. Here there's two, and you can see that these tangent lines are parallel to the secant line. All right, so it's really important that you only apply this when it's continuous and differentiable. We saw this with the intermediate value theorem. That one only needs continuity, but this one needs both continuity and differentiability. All right, so always make sure you're checking those before you apply the mean value theorem. All right, so why is it important that it's continuous and differentiable? This is a continuous function, but it's not differentiable right there. All right, why is it not differentiable right there? Hopefully you can recognize that's a cusp. And at cusp, we don't have a derivative. All right, so we try to find a secant line. All right, so this is my secant line. There's no way I'm going to find a tangent line that's parallel to that because all the tangent lines on the left-hand side of my graph are like that. All the tangent lines on the right-hand side of my graph are like that. All right, so it's important that it's differentiable because if these tight corners can kind of avoid the mean value theorem. So make sure it's also differentiable. Intermediate value theorem, just continuous. Mean value theorem, continuous and differentiable. All right, so here's an AP style question. We have this differentiable function. All right, notice it doesn't say anything about continuity, but we know if a function's differentiable, it has to be continuous. So as long as it's saying the function's differentiable, that's good enough. All right, a lot of times I won't say differentiable and continuous because it's kind of extra words. The reason the definition says it two separately because one is on a closed interval, one's on an open interval, so it's like the very ends don't have to be differentiable. But if it's saying for the whole thing is differentiable, it also implies the whole thing's continuous. It's the fewest possible number of values such that the mean value theorem guarantees the derivative is equal to 6. Remember, the mean value theorem says that this is equal to an average rate of change. This is asking how many times is the average rate of change going to be 6, because that forces the mean value theorem to give you an instantaneous rate of change. All right. So let's look at our average rates of change. So we basically have to look at a bunch of pairs. From 1 to 3, we take the difference in our y values. over the difference in our x values, and we get 3. All right, so that doesn't imply we're going to get a derivative equal to 6. We can go from 3 to 5, and that's going to be a difference of 12 over 2. That's 6. So from 3 to 5, there has to be a c value in there with a derivative 6. All right, we can go from 5 to 7. That's going to be 11 over 2. That's not 6, so that doesn't matter. And we can go from 9 to 7, or 7 to 9. And that's 13 over 2. It is not 6. All right, so that's just the 2 intervals. We also have to look at the bigger intervals, so we can go from 1 to 5. That's 18 over 4, which is not 6. We go from 3 to 7. That's 23 over 4. That's not 6. We can go from 5 to 9. That is 24 over 4, which is 6. All right, so that's another possible place from 5 to 9. And let's do the last one. We can do the graphs of 4, 1 to 7. That's 29 over 7. That's definitely not 6. We can do from 3 to 9. That is 36 over 6, which is 6. All right, so this one also looks like another one. And then we do the big one, 1 to 9, 42 over 9, and that's not 6. All right, so we have 3 different intervals where we got a average rate of change of 6. All right, so it looks like the answer should be D, but it's actually not the right answer. The actual right answer is 2. Why is that the case? Because from 3 to 5, there has to be a C from 3 to 5. There has to be a C from 5 to 9. And the third one looks like there has to be C from 3 to 9, but there's already 2 C's kind of covered in there. So this C here could actually be one of these 2. So it doesn't have to be a different one. It could already be this C or this C. So since this final big interval covers 2 smaller intervals that already had a C, we don't have to count that one, and that's why this one works. All right, we can talk about this one more in class if you're a little confused about why it's not 3, and I could like draw an example. But the basic idea is you look at the smallest intervals that are contained. The mean value theorem can be applied to which of the following functions? So again, this just means we're looking for functions that are continuous and differentiable. Is 1 over sine of x going to be continuous? No, because when I plug in 0 into sine, I get 0, and I would get 1 over 0. X minus 1 over the absolute value of x minus 1. All right, whenever you have absolute values, they look like they could cancel. On one side of the absolute value, you're going to get a negative number. On the other side, you're going to get a positive number. These have jumps, so there's a jump here at positive 1. That's not good. This one, you would have asymptotes at positive and negative 6. Positive and negative 6 are outside of the region I care about, so this one might be good. This one, you're going to have asymptotes at positive and negative 2, which are in the region I care about. So this one has asymptotes, so it's not continuous, which means the right answer is C. So C is not always differentiable and continuous, but in the region I care about, it is. And last one, all right, this one, a lot of words, so maybe you can pause it and read. All right, but it says we have this continuous on the closed interval and differentiable on the open interval. So right away, you can tell it's trying to lead you to the mean value theorem. All right, based on the graph, where are the x values that satisfy the mean value theorem? So remember, the mean value theorem says the secant line, if it's continuous and differentiable, there's going to be tangent lines which are parallel to it. So I have a tangent line here that's parallel and a tangent line there that's parallel. So the values that satisfy the mean value theorem are x1 and x5. All right, so C is going to be our right answer. All right, the instantaneous rate of change, the tangent line, is equal to the average rate of change, the secant line. All right, the mean value theorem is mainly used in free response questions. All right, so just make sure that you are looking for being continuous and differentiable, and you're saying you're doing the mean value theorem if you're using it. We've also learned the intermediate value theorem, which only requires continuity. I will talk about this a lot more once we get to our free response unit.